Introduction to Elliptic Curve Arithmetic. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring one of the most fascinating and important topics in modern cryptography: elliptic curve arithmetic over finite fields. This mathematical foundation powers much of today's secure communication, from Bitcoin transactions to TLS encryption on the web. But don't worry if that sounds intimidating. We're going to work through everything step by step using small, manageable numbers so you can see exactly how each operation works. Elliptic curves are special types of mathematical curves that have unique properties, making them perfect for cryptography. When we work with these curves over finite fields, meaning we do all our arithmetic modulo a prime number, we get a system that is easy to compute in one direction but extremely hard to reverse. This one-way property is the foundation of public key cryptography. Throughout this presentation, we will use concrete examples with actual numbers. We will compute every step explicitly, showing all the modular arithmetic reductions. We will not skip any steps or use simplified placeholders. By the end, you will understand exactly how points are added and doubled on elliptic curves, and how we can multiply a point by a scalar to create cryptographic keys. Setting up our elliptic curve. Let's start by defining our elliptic curve. An elliptic curve in short Weierstrass form has the equation y squared equals x cubed plus ax plus b. Here, a and b are coefficients we choose to define our specific curve. We need to work over a finite field, which means we choose a prime number p and perform all our arithmetic modulo p. This constrains all our numbers to be between 0 and p minus 1. For our example, we'll use p equals 19 as our prime modulus. This is small enough that we can verify all calculations by hand, but large enough to demonstrate the concepts. Now we need to choose values for our curve coefficients a and b. We'll pick a equals 2 and b equals 3. These are arbitrary choices that give us a valid curve with manageable arithmetic. So our complete curve equation is y squared equals x cubed plus 2x plus 3, and all operations are performed modulo 19. There's one critical constraint we must check. The curve must be non-singular. This means it can't have any cusps or self-intersections where the curve crosses itself. A singular curve doesn't have a well-defined group structure, which makes it unusable for cryptography. To check this, we use the discriminant formula from algebraic geometry. The discriminant tells us whether the cubic polynomial on the right side of our equation has any repeated roots. If it does, the curve has a singularity. Here's where the naming gets a bit confusing, so pay careful attention. In the general theory of cubic polynomials, mathematicians write a standard cubic as x cubed plus capital P times x plus capital Q. The discriminant of this general cubic is negative 4 times capital P cubed minus 27 times capital Q squared. Now, when we apply this to our elliptic curve, the cubic polynomial on the right side is x cubed plus x plus b. Comparing these forms, we see that capital P in the general formula corresponds to our curve coefficient a, and capital Q corresponds to our curve coefficient b. So the discriminant becomes negative 4a cubed minus 27b squared, or we can just check that 4a cubed plus 27b squared is not 0. For our specific curve with a equals 2 and b equals 3, let's compute. 4 times 2 cubed is 32, and 27 times 3 squared is 243. Adding these gives 275. When we compute 275 modulo 19, we get 275 minus 14 times 19 equals 275 minus 266 equals 9. Since 9 is not 0, our curve is valid and non-singular. This curve exists in a discrete space with only finitely many points. Unlike curves over real numbers which are smooth continuous lines, Our curve consists of discrete points where both x and y coordinates are integers between 0 and 18. Finding and verifying points on the curve. Now that we have our curve defined, we need to find points that actually lie on it. A point on an elliptic curve is simply a pair of coordinates, x, y. Both x and y are integers in our field. Specifically, between 0 and 18 for our case, where p equals 19. And these coordinates must satisfy our curve equation when we substitute them in. Let's verify that the point 1, 5 is on our curve. We substitute x equals 1 and y equals 5 into our equation. Y squared equals x cubed plus 2x plus 3, all modulo 19. The left side of the equation is y squared, which is 5 squared equals 25. Now, we reduce 25 modulo 19, 25 minus 19 equals 6. So, the left side equals 6. Now, for the right side, x cubed plus 2x plus 3 equals 1 cubed plus 2 times 1 plus 3. This resolves to 1 plus 2 plus 3, which equals 6. The right side also equals 6. Since both sides equal 6, the point 1, 5, is indeed on our curve. This verification process is crucial in elliptic curve cryptography. We must always verify that points we are working with actually satisfy the curve equation. We can find another point, 9, 16. Let's verify it. For the left side, 16 squared equals 256. Then, 256 modulo 19 is 256 minus 13 times 19, which is 256 minus 247, resulting in 9. For the right side, 9 cubed plus 2 times 9 plus 3 equals 729 plus 18 plus 3, which totals 750. Next, for 750 modulo 19, 750 divided by 19 is 39 with a remainder. So, 750 minus 39 times 19 equals 750 minus 741, which also equals 9. Since both sides equal 9, the point 9, 16 is also on our curve. Understanding point addition. Where the formulas come from. Point addition is the fundamental operation in elliptic curve arithmetic. When we add 2 points P and Q on the curve, we get a third point R that is also on the curve. I will explain what x sub 3 and y sub 3 actually mean, and where these formulas come from, because they are not arbitrary at all. First, let's discuss the notation. When we write P equals open parenthesis x1, y1 close parenthesis and Q equals open parenthesis x2, y2 close parenthesis, and we compute P plus Q, we get a result point R equals open parenthesis x3, y3 close parenthesis. The subscript 3 simply means the third point. We have point 1, point 2, and their sum is point 3. So, x3 and y3 are simply the coordinates of the result. The geometric interpretation over real numbers is beautiful. Draw a line through P and Q, find where it intersects the curve a third time, then reflect that point over the x-axis. But over finite fields, we can't draw anything, we need algebra. Here's how we derive the formulas. The line through P and Q has equation y equals lambda x plus c, where lambda is the slope. The slope is rise over run. Lambda equals y sub 2 minus y sub 1, divided by x sub 2 minus x sub 1. But in modular arithmetic, division means multiplying by the modular inverse. So lambda equals y sub 2 minus y sub 1, times the inverse of x sub 2 minus x sub 1, all modulo P. Now here's the crucial algebraic step. This line intersects the curve at 3 points. We already know 2 of them. P and Q. To find the third, we substitute the line equation into the curve equation. The curve is y squared equals x cubed plus ax plus b. The line is y equals lambda x plus circa. Upon substitution, we get lambda x plus c squared equals x cubed plus ax plus b. Expanding the left side, Lambda squared x squared plus 2 lambda cx plus c squared equals x cubed plus ax plus b. Rearranging to standard form. X cubed minus lambda squared x squared plus open parenthesis a minus 2 lambda c close parenthesis x plus open parenthesis b minus c squared close parenthesis equals 0. This is a cubic equation in x, and it has three roots. The x-coordinates of our three intersection points, x sub 1, x sub 2, and x sub 3. Here's where Vieta's formulas come in. For a cubic equation, x cubed plus bx squared plus cx plus d equals 0, with roots r sub 1, r sub 2, and r sub 3. Vieta tells us that the sum of the roots equals negative b in our cubic. The coefficient of x squared is negative lambda squared. So, x sub 1 plus x sub 2 plus x sub 3 equals negative of negative lambda squared, which simplifies to lambda squared. Solving for x sub 3, we find that x sub 3 equals lambda squared minus x sub 1 minus x sub 2. That's where the formula comes from. We square lambda because when we substituted y equals lambda x into y squared, we got open parenthesis lambda x close parenthesis squared, which equals lambda squared x squared. This lambda squared became the coefficient that determines the sum of the roots. Point addition. Complete worked example. Let's add two actual points on our curve. P equals 1, 5 and Q equals 9, 16. We'll show every single calculation and modular reduction. First, we need to compute lambda, the slope. Lambda equals y2 minus y1 times the inverse of x2 minus x1, all modulo 19. Let's compute the numerator. y2 minus y1 equals 16 minus 5 equals 11. Now the denominator. x2 minus x1 equals 9 minus 1 equals 8. So we need lambda equals 11 times the inverse of 8, modulo 19. To find the inverse of 8 modulo 19, we need a number that when multiplied by 8 gives 1 modulo 19. We can test values or use the extended Euclidean algorithm. Testing. 8 times 12 equals 96, and 96 modulo 19 equals 96 minus 5 times 19 equals 96 minus 95 equals 1. So the inverse of 8 is 12. Now we can compute lambda. 11 times 12 equals 132. We reduce 132 modulo 19. 132 divided by 19 equals 6 with a remainder. So, 132 minus 6 times 19 equals 132 minus 114, which equals 18. Therefore, lambda equals 18. Next, we compute x3. Lambda squared minus x1 minus x2, all modulo 19. Lambda squared is 18 squared equals 324. Now, 324 minus 1 minus 9 equals 314. To reduce 314 modulo 19, 314 divided by 19 equals 16 with remainder. So 314 minus 16 times 19 equals 314 minus 304 equals 10. So x3 equals 10. Finally, we compute y3. Lambda times x1 minus x3 minus y1 modulo 19. First, x1 minus x3 equals 1 minus 10, which is negative 9. In modular arithmetic, we add p. Negative 9 plus 19 equals 10. Now lambda times 10 equals 18 times 10 equals 180. Then 180 minus 5 equals 175. Reducing 175 modulo 19 to 175 divided by 19 equals 9 with remainder. So 175 minus 9 times 19 equals 175 minus 171 equals 4. Therefore, the result of P plus Q is the point 10, 4. Point doubling formulas. Point doubling is a special case of point addition where we add a point to itself. 2p equals p plus p. We can't use the regular addition formulas because when p equals q, the denominator x2 minus x1 becomes 0, which has no modular inverse. Instead, we use formulas based on the tangent line to the curve at point P. The doubling formulas for P equals x1, y1 are similar in structure to addition, but with a different lambda. For doubling, lambda equals 3 times x1 squared plus a, times the inverse of 2 times y1, all modulo P. This formula comes from implicit differentiation of the curve equation. We are finding the slope of the tangent line at point P. The numerator, 3 times x sub 1 squared plus a, represents the derivative of the right side of our curve equation with respect to x. If you differentiate x cubed plus ax plus b, you get 3x squared plus a. The denominator, 2 times y sub 1, comes from the derivative of the left side y squared, which is 2y. Once we have lambda, we use it just like in regular addition. X sub 3 equals lambda squared minus 2 times x sub 1, and y sub 3 equals lambda times x sub 1 minus x sub 3 minus y sub 1, all modulo P. Note that we subtract 2 times x sub 1 instead of x sub 1 plus x sub 2, because both points are the same. Point doubling is particularly important in cryptography because it is the building block of scalar multiplication. When we want to compute, for example, 27 times p, we do not add p to itself 27 times. Instead, we use a binary method that involves repeated doubling and occasional adding. This makes scalar multiplication much faster, logarithmic time instead of linear. Point doubling. Complete example. Let's double the point p, which is 1, 5, on our curve where a equals 2 and p equals 19. We need to compute 2p first. We calculate lambda. Lambda equals the quantity 3 times x sub 1 squared plus a, multiplied by the inverse of the quantity 2 times y sub 1, all modulo 19. Let's compute the numerator. 3 times 1 squared equals 3 times 1, which equals 3. Then, 3 plus a equals 3 plus 2, which equals 5. So, the numerator is 5. Now the denominator. 2 times y sub 1 equals 2 times 5 equals 10. We need the modular inverse of 10 modulo 19. Testing. 10 times 2 equals 20, and 20 modulo 19 equals 20 minus 19 equals 1. So the inverse of 10 is 2. Therefore, lambda equals 5 times 2 equals 10. Next, we compute x3. Lambda squared minus 2 times x1, all modulo 19. Lambda squared is 10 squared equals 100. Then 100 minus 2 times 1 equals 100 minus 2 equals 98. To reduce 98 modulo 19, 98 divided by 19 equals 5 with remainder. So 98 minus 5 times 19 equals 98 minus 95 equals 3. Therefore, x3 equals 3. Now we compute y3. Lambda times x1 minus x3 minus y1 modulo 19. First, x1 minus x3 equals 1 minus 3 equals negative 2. Adding p gives negative 2 plus 19 equals 17. Now lambda times 17 equals 10 times 17 equals 170. Then 170 minus 5 equals 165. Reducing 165 modulo 19 to 165 divided by 19 equals 8 with remainder. So 165 minus 8 times 19 equals 165 minus 152 equals 13. Therefore, 2p equals 3, 13. We've successfully doubled our point. Scalar multiplication overview. Scalar multiplication is the operation of adding a point p to itself k times, written as kp. This is the most important operation in elliptic curve cryptography. When you generate a Bitcoin address or a TLS private key, you're essentially picking a random large number k and computing kilogram, where g is a standard generator point. The result kilogram becomes your public key. Naively, we could compute kp by adding p to itself k times p plus p plus p and so on. But if k is a 256-bit number, common in cryptography, that would require about 10 to the power of 77 additions, completely impractical. Instead, we use a clever algorithm called double and add, which is based on the binary representation of k. The idea is this: any integer can be written as a sum of powers of 2. For example, 5 equals 4 plus 1, or in binary, 1 0 1. So, 5p equals 4p plus p. We can compute 4p by doubling twice, 2p, then 2 times 2p equals 4p. This way, computing kp requires only about log base 2 of k doublings plus the number of 1 bits in k additions, much faster than k additions. We'll demonstrate this with 5p where p equals 1, 5. The binary representation of 5 is 1 0 1, which means 5 equals 4 plus 1. So 5p equals 4p plus p. We start by computing 2p, then double it to get 4p, then add p to get 5p. This systematic process is what makes elliptic curve cryptography practical. Scalar multiplication. Computing 5p. Let's compute 5p where p equals 1, 5 using the double and add algorithm. We write 5 in binary. 5 equals 1 0 1 in binary. This means we need to compute 4p plus p. Let's work through it step by step. Step 1. We already computed 2p in our doubling example. We found that 2p equals 3, 13. Step 2. Now we need to compute 4p equals 2 times 2p. We double the point, 3, 13. Using our doubling formula with x1 equals 3 and y1 equals 13, we compute lambda. The numerator is 3 times 3 squared plus 2 equals 3 times 9 plus 2 equals 27 plus 2 equals 29. Reducing 29 modulo 19 gives 29 minus 19 equals 10. The denominator is 2 times 13 equals 26, which modulo 19 is 26 minus 19 equals 7. We need the inverse of 7 modulo 19. Testing. 7 times 11 equals 77, and 77 minus 4 times 19 equals 77 minus 76 equals 1. So the inverse is 11. Therefore, lambda equals 10 times 11 equals 110, and 110 modulo 19 equals 110 minus 5 times 19 equals 110 minus 95 equals 15. Now, x sub 3 equals 15 squared minus 2 times 3. That equals 225 minus 6, which equals 219. And 219 modulo 19 equals 219 minus 11 times 19. That equals 219 minus 209, which equals 10. Then, y sub 3 equals 15 times the quantity 3 minus 10, minus 13. First, 3 minus 10 equals negative 7, which modulo 19 is negative 7 plus 19, which equals 12. So, 15 times 12 equals 180. Then, 180 minus 13 equals 167. And 167 modulo 19 equals 167 minus 8 times 19. That equals 167 minus 152, which equals 15. So, 4p equals the pair 10, 15. Step 3. Finally, we compute 5p equals 4p plus p equals open parenthesis 10, 15 close parenthesis plus open parenthesis 1, 5 close parenthesis. Using point addition. Lambda equals open parenthesis 5 minus 15 close parenthesis times open parenthesis 1 minus 10 close parenthesis inverse equals negative 10 times negative 9 inverse. In modular arithmetic, negative 10 modulo 19 is 9, and negative 9 modulo 19 is 10. The inverse of 10 is 2. We computed this earlier, so lambda equals 9 times 2 equals 18. Wait, Let me recalculate. We have open parenthesis 5 minus 15 close parenthesis equals negative 10 equals 9 modulo 19. And open parenthesis 1 minus 10 close parenthesis equals negative 9 equals 10 modulo 19. The inverse of 10 modulo 19 is 2. So lambda equals 9 times 2 equals 18. Then x sub 3 equals 18 squared minus 10 minus 1, which simplifies to 324 minus 11, resulting in 313. Now, 313 modulo 19 is found by subtracting 16 times 19 from 313. So, 313 minus 304 equals 9. And y sub 3 equals 18 times the quantity 10 minus 9, then minus 15. This simplifies to 18 times 1 minus 15, which is 18 minus 15, resulting in 3. Therefore, 5p equals open parenthesis 9, 3 close parenthesis. The extended Euclidean algorithm. The extended Euclidean algorithm is the key tool for computing modular inverses. When we need to find the inverse of a modulo p, in other words, a number x, such that a times x modulo p equals 1, we use this algorithm. It is based on the classical Euclidean algorithm for finding greatest common divisors, but extended to keep track of linear combinations. The algorithm works by repeatedly dividing and taking remainders, just like the regular Euclidean algorithm. But at each step, we also express the remainder as a linear combination of the original two numbers. Starting with r0 equals p and r1 equals a, we compute r2 equals r0 minus q1 times r1 where q1 is the quotient. We continue until we reach a remainder of 1, which confirms that the greatest common divisor of a and p equals 1, meaning a has an inverse. The magic happens in the back substitution. Once we've computed the remainders down to 1, we work backwards to express 1 as a linear combination of a and p. Something times a plus something times p equals 1. The coefficient of a in this equation is exactly the modular inverse we're looking for. If the coefficient is negative, we add p to make it positive. Let's work through a complete example. Finding the inverse of 8 modulo 19. We start with the divisions. 19 equals 2 times 8 plus 3. Next, 8 equals 2 times 3 plus 2. Then, 3 equals 1 times 2 plus 1. And finally, 2 equals 2 times 1 plus 0. The last non-zero remainder is 1, confirming that GCD of 8, 19, equals 1. Now we back substitute. From the third equation, 1 equals 3 minus 1 times 2. Substituting for 2 from the second equation, 1 equals 3 minus 1 times, open parenthesis, 8 minus 2 times 3, close parenthesis. This equals 3 minus 8 plus 2 times 3, which simplifies to 3 times 3 minus 8. Substituting for 3 from the first equation, 1 equals 3 times, open parenthesis, 19 minus 2 times 8, close parenthesis, minus 8. This equals 3 times 19 minus 6 times 8 minus 8, which simplifies to 3 times 19 minus 7 times 8. Rearranging. Negative 7 times 8 plus 3 times 19 equals 1. In modular arithmetic modulo 19, we ignore the 3 times 19 term, so negative 7 times 8 equals 1 modulo 19. Since negative 7 plus 19 equals 12, the inverse of 8 modulo 19 is 12. We can verify. 8 times 12 equals 96, and 96 modulo 19 equals 1. Perfect. Thank you for your attendance. Please consider subscribing to the channel.